Python to cycle through a number of items or until a condition is met. The two primary ones are the for and the while loop. There's just an example here on the right. Here's for I in range 5. It's going to cycle through and print 0, 1, 2, 3, 4. And then similarly, here's an example of a while loop. You do that loop until a certain condition is met. In this case, until I is less than, while I is less than 5. We're going to use loops to solve the Euler's method and be able to solve this differential equation. We're going to come up with something like this in the end and show the analytical versus Euler's method, and we'll use a loop to do it. If you'd like to follow along with this example, the Google Colab or the is available right here on 263 website. Just come here to schedule, and then this is going to be Colab 5. If you just select that, it'll open up in a new browser window and you can follow along with this. So let's first of all just create a new loop for I in range, okay, and then we could do 3, and then we could print I. So that's going to give us 3 values. It's going to do 0, 1, and 2. But let's say we wanted to instead we wanted to do 0, 1, 2, 5. Okay, that's going to start at 1 and then go up to 4. It always does 1 less than this final value right here. And so there are 4 values there. And so if you just leave off the 1, then it's going to start with 0 by default. Okay, you can also say what increment you want in the range. And so let's say I want to do increment 2. Then it's going to print every odd number, 1, 3, 5, 7, and 9, and it won't include the 10. Even if I went up to 11, okay, it wouldn't include that either. Okay, it always does 1 less than what you put there. Alright, so let's also just put in a list. So here's how you use range to create this loop. Tells it how many times it needs to go through there. But let's say I just had, for example, in this list, I had a list of items I needed to buy from like the grocery store, bananas and apples and let's say potatoes. Okay. Alright, so there it goes through and just cycles through this list. It goes each one and then I print it. And it goes back through, and then I becomes the next item in my list, and so it goes on. So I could do this as 1, 2, 3, 5, for example, and then it's going to print those. So the range is just an easy way for us to do, something like I need 5 values, and then it's just going to cycle through those 5 times. Okay, and the other way to create a list is through a while loop. And then we'll go back and do these in just a little bit. But a while loop is just very similar here. You need to define the condition. So if I is less than 5, then I'm going to print I. Now if I hit enter at this point right here, it would cycle through an infinite number of times until it would never terminate the condition. So I need to increment I here. I equals I plus 1, or in short, you can do I plus equals 1, and then it's going to print just like we did with the range 5. It's going to print out those first 5 numbers of that list. Okay, so I could also change this condition, and so while loops are really useful if you don't know when you need to stop the loop beforehand, versus the for loop is very convenient if you know exactly how many times you need to go through the loop and what are those conditions. Okay, so let's go back up here and just create a loop that prints all even numbers between 1 and 11. Okay, so I'm going to go 1. In this case, I'll just start with 1 and go to 11. Okay, and I could do, in this case, I would do, I'd do 12 because it's not going to include that very last one. And then I could have an if statement here, if I mod 2. So if you divide I by 2 and the remainder is 0, then I'm going to go ahead and print I. Okay, let's see, that did not work. I had 1, 3, 5, 7, 9, 11, but I wanted to do the even numbers instead. Okay, so that one I need to say if it's equal to 0, because this one's going to choose be a 1 if it's odd. So that was a true statement. So I need to just do I is less or is equal to 0 for that mod statement. Okay, so there I have 2, 4, 6, 8, and 10. Those are all the even numbers. Okay, so conditional statement here, I did the modulus or the mod function, and then I said if that's equal to 0, if the remainder is equal to 0 when you divide by 2, and then I just printed the I. Okay, so let's go on to the next one. Create a while loop that generates and prints a random number between 0 and 10 with np numpy random.randint. Okay, and we'll stop when the number is equal to 7. So in this case, I'll just say I is 0. I'll just start that out, and then if while I does not equal 7, okay, so the exclamation mark equal, that's going to be the not equal. Okay, let me make this just a little bit bigger so it's easier to see. Alright, and then we want to assign our new I value. So I is going to be numpy dot random randint, and that will be between 0 and 10. And I think we also need to import numpy. Okay, so let's just run this. Oh, I need to probably print I here. Okay, so these are all the values that it went through, and it eventually got to 7. That's a surprising number of times it had to generate that random integer before it got there. But you can see once it generated 7, then it said that this condition, well, this condition became false, and so it stopped and then proceeded on to the next point. I'll go ahead and just print here finish. So this one only took 4, okay, or 3. Alright, so here you could see it went through until I was equal to 7, and then it terminated and then came outside of the loop. So the one thing you'll notice here is that indentation is very important in loops. It tells Python how many, what statements are part of this loop, and then once the loop is done, it goes on to the next statement. Okay, so let's go on down to the next one. This is going to be a first order reaction. It is an A goes to B and has this reaction rate right here, where Ca is the concentration and T is the time, and K is going to be the reaction rate constant. Now you do have an analytic solution to this for very simple differential equations. You do have an analytic solution for those, and so here it shows the this is the procedure for solving that. If you have done a differential equation class, you'll know that you have your original, you separate the CAs onto one side and the time onto the other side, and then you integrate both sides, and then you solve it, you integrate it, and then do the limits of integration here. Okay, so this is just kind of a review for solving the differential equations. We'll solve it, and then we come up with an analytic solution. Okay, so there's our solution for this very simple differential equation. And so let's just go ahead and first of all solve this. Just set it up and be able to compare with our numerical solution. So we have an analytical or an exact solution, and we're going to compare it with the numerical solution. So let's go ahead and just first of all create the final time is going to be equal to this was 7, and the initial concentration is going to be 5. Okay, and then the K value was equal to 1. Alright, and then we need to have some of our times here. I'll just say time equals linspace between 0 and the final time, and you could put as many points as you want in there, just go with the default of 50. And then we have CA equals CA naught times the EXP of minus K times TM. Okay, and then we can just print CA to look at those. Okay, so this is our analytical or exact solution. And then we're going to use a method called Euler's method with a loop to compare to this exact solution. Okay, so Euler's method, it's a simple numerical technique to calculate the solution of a differential equation. We're going to essentially just be approximating the derivative with a finite difference, and you can do this in a forward or an implicit or an explicit form. We're going to use the explicit form for the Euler's equation. So we're going to substitute this derivative in for our differential equation, and then we'll just solve for the next CA value. Okay, so we've just got to rearrange this, and we're going to use a loop as we as we go through this. Okay, so Euler's method. Let's just go ahead and do CA, and then I'll say E for Euler's method, and I'll just say that that's going to be an empty array of n values. And so let's just say we had n, let's say 14 steps is the thing that we need, so n is going to be equal to 15 because we also have our initial condition. Okay, so we're going to store the values right there, and if I knew my initial condition, I could just put initialize this as 1s and then just do CA naught. Okay, so I'm just going to give all of the values a value of equal to 5, and now I'm going to loop through. I know how many times I need to loop through this for I in range 1 to n. Alright, and I'm going to loop through this, so CAE is of my I value is going to be a function of what came before it, and so then I just do CAE I minus 1. Okay, that's this part right here, and then I'm going to subtract K times CAE I minus 1 times the delta T, whatever my delta T value was. And so let's just specify that as well as 0.5. Okay, and so here is CAE. Here are my values from the Euler's method. Now let's go ahead and create this plot and show what are the values graphically. And so if I come down here, I can just say mat plotlib inline. You won't need to do this line in Google Colab. And then I'm going to import matplotlib.pyplot as plt, and then we'll plot the two things that we want are going to be the time and the CA value, and let's just make that a red line. Okay, so there's our exact solution, and then we also want the Euler's method on there, and so I'll do TME, and then CAE, and then let's make that a black circle, and we need to define TME as well. We can either do linspace or we can do a range, which says we want to go between 0 and final time, and then we want, let's see, I believe it's 0.5 was our DT value. Let's just print this. I think there's going to be an error. Let's just print because I need one more value in here. Okay, so I need to get 7 in here as well. So I just add a little bit more so it hits that 7. Okay, and here you can see the plot. you can have you can show the Euler's method versus the exact solution. So there's a little bit of a difference there. Let me just show you how to do this as well with an ODE integrator, which is going to control the error for you. Okay, so we're going to get on to this one where we adjust the step size and make it more accurate, but an ODE integrator will also do that for you. I'll just come back up here, and if you create a new function, so for example dca dt as a function of ca and time, and then we just return what's on the right hand side, the derivative part of it, calculating the derivative. And then if we just said ca ode int, and I'm just going to use the ode int function, I'll import that in just a second. And then we need our times that we want. I'll just put tm in there. So if we do something like from scipy.integrate import ode int, and then rerun this, I'm going to have a ca ode int solution as well. Just go ahead and put that on the same plot. Okay, tm and ca from ode int, and I'm going to make that a black dashed line. Okay, so you can see that matches up very well with the solution. One of the things that ODE integrator does is it adjusts the step size for you to maintain accuracy, and uses also a higher order method than Euler's. So let's come down here and just see if we can do this ourselves. We can build an adaptive step size. So instead of delta t equals 0.5, we're going to increase this. We might get something like this, but we could also decrease it as well and get more accuracy. So let's come up here and just copy our Euler's method, and then we'll just adjust the number of steps that we need until we get the accuracy that we need as well. So I'm going to increase, in this case I'm going to increase the dt to 1.5, and we'll create this one's going to be, I'll just say it's going to be 1, and then we'll do another one as well, just to be able to store it so we can plot them all together. Okay, so here's 1.5, and let's see, we need to also do another time. I'll do time 1, and that's going to be a range, and then we're going to go between 0 and time final. Now I'll do 0.01. Okay, and then we'll have the dt there. Alright, so for I in range, for I in tm1, we'll go through each of these until it doesn't, it's going to cycle through each of them. Okay, and we want to do -1 because we don't want the initial condition. And then let's see, I'll say ti, and then I equals, start off with 1. Okay, and then I plus equals 1. Alright, so let's just go ahead and run through this one, and then we'll plot it and include it on our plot. And I'll take all of these values right here. I don't need to import matplotlib again, but I'll just include these on the plot, and then we'll compare it with changing the step size to 1.5. Okay, so there's our original one, and we'll just add on to this one. We're going to add our tm1 and cae1, and then let's add this one as a let's say green X. Okay, let's see. This one had an error here. Let's just see what this error is. Okay, they have different shapes here. I think I changed those. Oh, there it is. I need to change this to TME1. Okay, and TME1. Okay, and that's going to have another error because then I redefined TME. So let me just come up here and rerun this one. And this one has an error as well. Okay, so I'm not managing my data shapes very well here. Okay, I'm going to just come back up here. I've just rerun all of these cells. I just redefined some of the values down below. So I just got into an issue where I had rerun some of these cells and redefined some of the variables, and then when I run them in different orders, it causes an error. So I'm just going to come down here. You know, this one doesn't look, I'm not managing my arrays very well. So let's just go ahead and start this one over. I'm just going to use you know, this A range, but then I'm going to just do something like this where I have you know, the 0.5, and then let me do this as well for the 1.5. I'll just change that. I'm going to call this one the T3 and the CAM3. Okay, and that's going to be our 1.5, and then if we also include one more for the 2.1, then I'm going to have something like this. And I'm just going to run through the loop, go from 1 to n, and I have this A range up here that defines my times, and then here's my n value. And then I'm going to store it in CAM2 and then give it the initial condition, and then as I loop through, then I give it the new CAM2. I do that for CAM3 and CAM4 as well. Okay, and then when I want to include this on a plot together, I can then come back up here and copy this, and let me go ahead and just put all of these onto one plot. And so here is my original plot, and I don't think I need this one there. Okay, original plot, and with the CA Euler's method, but now I have a new I also have that recalculated here with T2, okay, T2 and CAM2, and so if I rerun that again, I get the same solution. And then I'm just going to copy this for the other two as well, CAM3 and CAM4, and there we go. I'll just change the symbols. We'll do a let's see, an X, and make that color orange, and then we'll change this one to a black square. Okay, so we could see that you know, these you know, if I wanted to include a line here as well, you can see how these connect. Okay, so you can see that these are not very accurate, but if I wanted to increase the accuracy, let's say I wanted to do 0.1 instead of 0.5, and then I just rerun this one again, you can see that the black squares are now lining up with the analytical solution, and so as you decrease the step size, okay, you're going to get more accuracy. But in this loop, it's easy to do that. I just had to redefine one number here, and then it cycles through a different number of times. Now going back to the ODEant solution, it'll adjust that for you. Okay, so this is just an example of using a loop to solve a real problem. In this case, Euler's method to integrate an ODE. Okay, next problem we're going to do is going to be a much more complicated. There are going to be 4 differential equations instead of just the one, and we're going to use loops to do that as well.